Everyone, Dr. Chem here. If you've ever stared down at a completely dark, sludgy reaction flask and just wondered how on earth you're actually going to isolate that one brilliant microscopic molecule you need, well, you are exactly in the right place. Today's explainer is all about the ultimate physical technique for molecular separation, column chromatography. We're going to take this giant puzzle of molecular purification and break the whole thing down. We'll start with the high-level theory and take it all the way to practical, hands-on lab execution.
Okay, so I want to kick things off with a quote straight from the MIT Digital Lab Techniques Manual. It says, "The purification of chemicals is one of the most important jobs of a research chemist." And honestly, that perfectly captures the stakes of what we're looking at today. Because think about it, you can design the most elegant synthetic pathway in the world, but if you can't actually isolate your final product, you don't have a product. Mastering this technique isn't just some annoying lab requirement, it's literally a foundational survival skill in chemistry.
All right, let's dive into this roadmap for the explainer. We'll hit core principles first, move into choosing phases, walk through the actual lab workflow, discuss TLC monitoring, tackle some troubleshooting, and finally wrap up with real-world applications.
So kicking things off with part 1, the core principles.
If we look at the official IUPAC definition, chromatography is described as a physical separation technique. It's entirely based on how different components distribute themselves between two things, a stationary phase, which stays put, and a mobile phase, which flows through it in a specific direction. It's actually a pretty brilliant concept, and it dates all the way back to 1903. A Russian botanist named Mikhail Tswet first used it to separate colorful plant pigments. Fun fact, chroma means color, which is exactly how the technique got its name. So, what does this actually look like in practice? Well, you've got a vertical glass tube. That's your column. You pack it with a solid stationary phase, you carefully load your sample mixture at the top, and then you pour in your liquid mobile phase. You can really just think of the column as a microscopic obstacle course. Your molecules are flowing down, sure, but because they have different polarities and intermolecular forces, they interact with the stationary phase at totally different rates. Some of them breeze right past the obstacles, while others get snagged and move super slowly. That differential affinity is exactly what physically separates your chaotic mixture into distinct, pure bands. Now, depending on the specific materials you decide to use, this obstacle course works in slightly different ways. The two primary forms we usually see are adsorption and partition chromatography. In adsorption chromatography, your stationary phase is a solid, like silica gel, for example, and the mobile phase is a liquid. Here, the molecules physically bind or adsorb right to the solid surface. Partition chromatography is a bit different. In this case, the stationary phase is actually an immiscible solvent coated onto a solid matrix. The molecules separate by literally partitioning themselves between the two liquid phases.
Moving right along to section 2, choosing your phases.
What's really fascinating here is the absolute tug-of-war that completely defines chromatographic separation. Let's look at traditional normal phase chromatography first. Here, your stationary phase, which is usually silica, is highly polar, and your mobile phase is nonpolar. Now, because like attracts like, any polar molecules in your sample are going to stick tightly to that polar stationary phase and move down very slowly, while the nonpolar molecules just wash right on through. Reverse phase chromatography literally flips the script. The stationary phase is nonpolar, and the mobile phase is polar. Understanding this polarity dynamic is the secret to controlling exactly which molecules elute first. To fine-tune that tug-of-war, chemists use something called the allotropic series. Think of it as a cheat sheet of solvents, all ranked by their polarity. Let's say you want your compounds to move down the column faster. What do? You just increase the polarity of your mobile phase. You might move from a nonpolar solvent like hexane up towards something highly polar like methanol. Dialing in that perfect solvent system, which sometimes means mixing a very specific ratio of two different solvents, gives you absolute control over both the elution rate and how sharp your separation is. Okay, on to section 3, the lab workflow. Let's get into the actual physical steps. So, your very first physical move at the bench is loading your sample onto the column. You basically have two choices here. First is liquid loading, where you dissolve your mixture in a tiny amount of solvent and carefully pipette it right onto the top of the stationary phase. Or you can do dry loading, where you pre-adsorb your sample onto a bit of silica, dry it into a powder, and then just sprinkle it on top. Now, liquid loading is fast, and it's super common for highly soluble mixtures. But if your sample needs a really polar solvent just to dissolve, using that solvent can actually ruin your initial separation right out of the gate.
In those tricky cases, dry loading is absolutely the professional's choice to ensure you get incredibly sharp, narrow starting bands. Let's look at how this builds into the complete procedure. Step 1, you've got to pack the column. We highly prefer the wet packing method here, which is creating a smooth slurry of silica and solvent, mainly because it prevents trapped air bubbles and gives you a perfectly uniform bed. Step 2, load the sample, and do it gently. You do not want to disturb that perfectly flat surface of your silica. Step 3, continuously add your mobile phase eluent to drive the molecules down the column. And finally, Step 4, as the liquid emerges from the bottom, you collect it in small separate containers called fractions.
Which brings us to Section 4, TLC monitoring.
Now, thin layer chromatography, or TLC, is your absolute best friend in the lab. Before you even think about packing a column, you run TLC plates to test out different solvent mixtures. What you're looking for is a solvent system that gives your target compound an RF value, that's the retention factor, of roughly 0.2 to 0.35. Once your column is actually running and you're collecting all those fractions, you spot those fractions onto new TLC plates. This basically acts as an X-ray, showing you exactly which tubes contain your pure target compound, which ones have impurities, and which are just filled with empty solvent.
Let's get real for a second in Section 5, troubleshooting. Look, things are going to go wrong in the lab. The crucial thing is identifying the physical signs of failure early. If you see air bubbles or cracks in your silica bed, you're going to experience something called channeling. That's where your solvent just rushes down the cracks instead of flowing evenly, which completely ruins your separation. Or, if your TLC shows overlapping bands colluting into the same fractions, you probably overloaded the column with way too much sample or maybe used a solvent that was too polar. And guys, the cardinal sin of column chromatography, letting the mobile phase drain completely below the top of the silica. If a column runs dry, the stationary phase cracks, and your separation is essentially done for. So seriously, keep adding that solvent.
And finally, Section 6, real-world applications.
So why put all this effort into mastering this technique? Well, because it scales massively and it literally drives modern science. Column chromatography isn't just for isolating a few microscopic micrograms of product for an undergrad grade. It's used on a massive industrial scale, processing literal kilograms of material. It's the backbone of purifying organic synthesis products. It allows researchers to isolate delicate, completely unknown natural products from plant biology. And honestly, it is a critical purification step in manufacturing the life-saving pharmaceutical drugs that are used globally every single day.
All of which leaves us with this final thought. You now know the theory, you know the workflow, and you know the troubleshooting required to separate the complex into the completely pure. So the very next time you're facing a muddy, complex mixture in the lab, I want you to ask yourself, how will you apply the principles of differential affinity to optimize purification in your own research? The Chemical Obstacle course is waiting for you. Get out there, choose your phases wisely, and please never let your column run dry. I'm Dr. Chem. Thanks so much for joining me on this explainer, and happy separating.